For this session, we will go through all the weekly problems set 9. Okay. So let's begin. Oh. Okay, so for the first question, we need to prove that R is not countable and R equals to Pn. And for the second, for the Pn part, it's already proved in the lecture 31. So if you don't know that, you can check that. And also, in lecture 31, we already know that the size of R equals to the size of the real number set from 0 to 1. So to prove this one is enough if we can prove that 0, 1 is not countable. So how to do that? Here we can suppose that this one is countable. So we can list this set as A0, A1, A2, blah, 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 blah. And let A0 equals to 0 point, let's see what, A00, A01, A02, blah, blah, blah. Something like this.
这题堂里面一共他妈就5个原子分和2个 TA。
Please mute yourself, please. Okay.
Yeah. 好的，根本不好。
Okay. Okay, let's go on. So for the similar thing, we can define some A1 and A2 and all of other elements inside this set. So now let's consider another element that's called something like B, where B equals to 0 point B, B0, B1, B2, blah, blah, blah. Where B0 is not equals to A00, B1 is not equal to A11, and so do that. So then we can find that B is not equals to any of the elements inside this this countable set. But B is of course inside the set 0, 1. So this means that the suppose 0, 1 is a countable set. It's wrong. It's wrong. And as this is wrong, this is true. As this is true, we know this one, so R is not countable. Okay, any question? If no, let's go to next question. Okay, now let's go to question 2. Okay, so basically we want to know what is R times R. And okay, we already know this one. So suppose we can prove that 0, 1 times 0, 1 is equals to 0, 1. Then it's equivalent to this part. This 2 is equivalent because we know that R with the same size with 0, 1. So the question is how to prove this part. Oh, sorry, how to prove this part. So basically, we want to find some bijection function takes it, let's say R1 and R2 equals to R3, which maps to the 0, 1 times 0, 1 to 0, 1. Oh, sorry. Something like this. Then how to do that? This is really easy because we can say that R1 equals to 0 point A0, A1, A2, blah, 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 and R2 equals to 0 point B0, B1, B2, blah, blah, blah. And then we can set R3 equals to 0 point A0, B0, A1, B1, A2, B2, and go on. So it's easy to find that this function is bijective, as if we give R3, we will find the unique R1 and R2. So as we got this function, we know that this one is true. And as this one is true, this one is true. Then we solve the problem too. Okay, let's go to question 3. Basically, we have this formula. And here I have two claims. I want to ensure that you know these two claims is true. The first is given some number n, and we have this formula k plus c0 plus c1 plus until ck equals to n. This equation have finite natural number solution because you can consider we have n pigeons and we want to put that into k plus 2 holes. Oh, sorry, yeah, not this case, but anyway, you can just assume that this one have finite natural number solutions here. And also another thing is that for any this kind of polynomial equation, if we set that equals to 0, then it have at most k roots. This equation, I hope you have learned this in maybe your high school or the previous math lecture. And this one called the uh, fundamental theorem of algebra. Yeah, something like this. So with these two claims, it's easy to find that you can list all the solution of this kind of equations in some order. And here is how I order them. You can have different other ways to order, but I can order this as this one. So first we want to got a list of equations as E. Then E is countable, right? Because we can list all the equations based on claim 1 with the order of claim 1 with increasing in. And for each equation, after we list each equations, then we can just solve that in some find all the find set of their solutions. We can list them as like SI for the solutions for the ice equation. So as SI is finite for all I based on the claim 2. And we know that the final set we want is the union of all possible SI. So this one is also countable. And then we are done of this question. Okay, if no question, let's go to next one. Here we know that X is countable and Y is not countable. We want to check if this one equals to this one. First, we can create a set called X prime, which contains all the elements that in X but not in Y. So suppose this one is empty, then that means X is a subset of Y. And this one and then X union Y is equals to Y, and this one is directly true. Then there are two different cases. Suppose this set is finite with k elements, and suppose this one is infinite. But both of cases can be done in the similar way. So let's first check the case if this one is infinite. As we know, X is countable. And as we know that X prime is a subset of X. And later we will prove that X prime is also countable. And as it's countable, we can list that X prime equals to X1, X2, X3, blah, 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 blah. And also we can find some list Y equals to Y1, Y2, Y3, blah, 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 blah. Note that as Y is not countable, so let's call this Y prime. So Y prime is subset of Y, and Y prime is countable. So you can use any way to construct such kind of Y prime, and any countable set there is okay. And then we want to construct some set called C, which equals to X1, Y1, X2, Y2, X3, Y3, and go on. So, and we can also call it C1, C2, C3, C4, and go on, something like this. And basically, you can find that C is countable because we already list it in this way. Then it's easy to construct a function called if for fx equals x if x is not in y. And sorry, if f is not in C, let's see, if x is not in C, and also fx equals to x prime equals to C2i if x equals to Ci. So this function, first of all, this function is bijective, right? Because C is infinitely countable. So this part, it is bijective, and this part is also bijective. And X can either not in C or equals to some Ci for some I. So it includes the domain includes all possible X in X, U, Y. And also let's check the range. Suppose this X is not in C. Then it means it's not some element inside the large X, because all the element in the large X is some element in C. So which means it's already in Y, and this Y is okay. And also, suppose X is in C, then we'll return something like in the even position in the C. For all the even position, it's Y1, Y2, Y3, and some Yi, which is inside Y. So this function maps the axial Y to Y, and this function is bijective in this case. So this gives us the conclude that equals to Y in this case. So we are done for this case, but what about it's finite? It's also easy. We can make C as x1, y1, x2, y2, and blah, 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 xk, yk, and then we got yk plus 1, yk plus 2, yk plus 3, and go on. And then we keep these two functions, it's still workable, and everything is not changed. Okay, any question for this? Okay, if no, let's go to next question. Firstly, let's consider something, the set called string, which contains all possible string. It's easy to find that this string is countable, because let's consider, suppose ni is the string with length I. We know that the number of ni is 2 power I, right? And for finite I, this number is finite, so this set is finite. And the set string equals to union of all the ni. So the string is countable. Then what about all the language set? A language can be any subset of a string. So we say that language set is just the power set of string. Or we can say that the power set of int, because we know that the set of string is the set of int. So this one is true. And remember that we have shown that in question 1, both of these two are true. So power set of n is not countable. Which means in this question, we know that the language set is not countable. Not countable. Okay, now let's consider if a Python program set can be countable or not. So any Python program can be represented as a binary file. I hope you know that as you are a CS student, right? Everything in the computer science can be represented as a binary sequence. And the binary sequence is just string. So we can see that P is the set of program, all possible program. So P is a subset of string, the binary string. Which means as string is countable, so P must be countable. And so we know that the size of P is smaller than the size of language. Let's say, yeah, something like this. Or let's say the language set is something like this. Here is the set of all possible language. Now let's check back what they want us to prove. They want us to prove that for all L inside, oh, so for us, exists some as, so that for as PS equals to true, denotes that S is inside. Support this L star. So make this L star is different with the language L. Okay, just give us, so let's use this one. Okay, so basically this means we can give a function f so that we can map this one to this one, right? Because if we give any language there, then we need to return a Unicode program so that it can check if this language is perfect language, something like that. Okay, so, and of course, this function should be one-to-one. Because no two language can share one program. Otherwise, these two languages should be, there's something that cannot check for one language. So as this one is true, so we know that this one must be smaller or equal to P. But we also know this one. These two are contradict with each other. So we cannot find this one, and which means that there not exist such kind of thing. Okay. Okay, seems no question. Let's go on. For question 6, let's first suppose that A is finite with n elements and give a function f map A to A, which we can consider it as we put n pigeons into n holes. And suppose this function is onto but not one-to-one. What is the onto function be like? We want each hole have at least one pigeon. But it's not one-to-one, so it means that at least two pigeons are in one hole. It's obviously that this one is not possible, right? To make both this to be true, at least need n plus one pigeons. Otherwise, it's not true. So if it's onto and A is finite, it's impossible. So we got that A is infinite. Okay, then suppose F is one-to-one but not onto. But not onto. What will happen there? Okay, as it's one-to-one, so we know that no two pigeons in one hole because it's one-to-one. But it's not onto, so that means that at least one hole have no pigeon. Similarly, is that possible? Of course not, right? For the first rule, that with n pigeons, we need n holes there. And as we only have n holes, so each hole should have at least one pigeon. So this one is not true. So similarly, this one is not true if A is finite, so A is also infinite in this case. Okay. Okay, now let's go to next question. Here we already know that A is infinite. So here are two cases. First, A is countable or A is not countable. If A is countable, then it's easy to find A equals to A1, A2, A3, and blah, 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 blah. We can list it as this kind of thing. And then if we want to create an onto function, that's called f is the onto function, then it's really easy, right? We can write that, let's say, fx, maybe let's write something like this. Yeah, fx equals to ai plus 1 for x equals to ai. So it's easy to check that this function is one-to-one but not onto, because there's no x in A can map to A1 because A1 is always the least function. the first element there. There's no A0 in this case. And if we want it onto, but not one-to-one, here we can write Gx equals to, let's say, A1 if X equals to A1, or AI minus 1 if X is not equals to A1. For this case, it's onto because for any element inside A, for any AI, we can find some X so that Gx equals to AI. Just like X equals to AI minus 1 or AI plus 1, something like this. But it's not one-to-one because we know that GA2 equals to GA1 equals to A1. So it's not one-to-one, but it's onto. Then what about A is not countable? It's also easy. Even A is not countable, we can find that A prime inside A, well, A prime is countable. So A prime is A1, A2, A3, and blah, 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 blah. And then we can give our fx as if x in A prime. Then we do the above thing. So return AI plus 1 for x equals to AI. And we can set a x equals to x if x not in A prime. So we can do this function is also it's one-to-one but not onto. With the same reason as yf is one-to-one but not onto. So with a similar way, we can create some gx equals to first x if x not in A prime. And then A1 if x equals to A1. AI plus 1 if x in A prime and x not equals to A1. So this one is onto but not one-to-one. Okay, then let's go to next question, question 8. Suppose A and B are infinite and A is inside B. Prove that if B is countable, then A is countable. We already used this. We already used this statement several times. So now let's try to prove that. So first, as we know that suppose A is countable, then we can find a bijective function A to N with 1 plus 1-to-1 with bijective. Yeah, sorry. So basically, it's really easy. As B is countable, we can list B as B1, B2, B3, and blah, 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 something like this. And then we can list A in the order of that appear in B. So we can list A1, A2, A3, and blah, 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 so that A1 equals to BI, or AI equals to maybe, okay, sorry, let's say something like AI equals to BJ and AK equals to BX, so that if I is smaller than K, then J is smaller than X. So basically, we list A in the order it appears in the set B in this order. And in this case, we can list all possible A there because A is a subset of B and B is countable. Then it's obvious that A is countable and that we can find this function. Just make N is the index of the element of A inside AI. Okay, and question for this one? James, no, let's go to the next question. Okay, we do it really quickly for this one. For question 9, here we have two set x and y. And we have one-to-one function f from x to y and a one-to-one function from y to x. One-to-one, but not onto. Both of these functions are like that. So basically, if we can separate x into two sets x1 and x2, and separate y into two sets y1 and y2, if we can find that fx1 to y1 is bijective, and gy2 to x2 is bijective, then we are done, right? Because we can for all the x in x1, we do f, and in all the x in x2, we do g inverse for x inside x2 to y2. Then we can easily combine these two and find this kind of thing. Here is how I do. Firstly, I define C0 as all the elements in X, which is not mapped by the function G. As G is not onto, so this set is not 0. And also we can write it like this, like all the set X minus all the possible range of Gy. And then I define a recursive equation like Ck equals to f Ck minus 1 and over G. Okay, this is as the argument of G. And I call the x1 set be all the union of Cf, all possible I. Like I goes from 0 to infinite. And x2 is x minus x1. y1 is the range of x takes the domain as x1. And y2 is y minus y1. So with these formulas, we successfully separate x into x1 and x2, y into y1 and y2. And now I need to prove this part. Firstly, let's consider the f thing. This one is already true, right? Because we got y1 directly from x1. So this is onto. And also, f is 1-to-1. Because if it's not, then the original f function cannot be 1-to-1. So in this case, we know that this first part is correct. Then how do the second part? To prove that this one is bijective, we need to show that it's onto and it's 1-to-1. 1-to-1 is already done, right? Because original G from Y to X is 1-to-1. So then, is that onto? Let's suppose G map from Y2 to X2 is not onto. Then that means exists some X inside X2. For all Y in Y2, Gy is not equals to X. Then there are two cases. For all Y in Y, in the original Y set, it's not mapped in, no one can map to X. If in this case, then let's go back to check the definition of C0. So if in this case, X should be inside C0, and in other words, X should be in X1. It cannot be in X2. So this case is not possible. Then the next case, Suppose exists some y in y1, gy equals to x. Then is that possible? As this one is true, then we know that exists some x prime inside x1, so that f(x prime) equals to y. Because this is the definition of y1, so this one must be true. And if this one is true, then let's say x prime is inside, say, let's say I for some I. Then say I plus 1 is equals to, let's see, what's that? Okay, here is the definition of recursive of ck. So say I plus 1 equals to g I ci. What happened to this? As we know that f(x prime) equals to y, so we know that y is inside ci. And as we know that gy equals to x, so x is inside g fci. What does this mean? This means x is inside ci plus 1, and which means x is inside x1. So it's contradicts to x inside x2. So this case is also not possible. So in other words, this function must be onto. Then as this is also onto, we prove this part. And then we are done. Okay. Now let's go to the last question. Okay. So X is the infinite subset of N. And let's say that Y is the finite subset of N. So X is the infinite subset. Let's denote Y as the finite subset. And we know that X union Y is equals to all subset of N, which is Pn. And we know that this one is not countable. So if we can prove that, if we can prove Y is countable, then what will happen? Let's suppose Y is countable. And then as we know that Pn is not countable, so do X U Y. So X must be not countable. And also, as Y is countable and X is not countable, so we know that X U Y is equals to X. And X U Y is equals to Pn. So X should be equals to Pn with the size. Okay. And as we know that R equals to Pn, which is already proved in lecture 33. So if we can prove this one, we can finish everything. So which means the only thing we need to do is we want to prove Y is countable. And this is kind of easy to prove, right? Because Y is finite subset of A. So let's suppose let's say denote Yn. Yn is subset contains n elements. And then Yn is smaller than n power n, right? Because in a tuple with n elements of natural number, it's possible that we have the same element. But in the Yn, it's not possible. So we know that this one is true. Or this one is true. And as we know that this one is finite, so this one is also finite. Yn is finite, and we know that y equals to or union of yi. So it's easy to show that y is countable with this way. And as y is countable, we know that, and as we just say that x union y is not countable, so x is not countable. And x union y is power set of n, so x is power set of n. This one is proved in question 4, I remember. Yes, it's what we do in question 4, so we can directly use that here. And as we know that the size of real number is same as the size of power set of n. So we know that x is also equals to the power set of n. And then we are done. Okay, this is all about this week's weekly problem set. Okay, there's some question for question 3. Okay, let's go back. Question 3. Okay, so first of all, the two climb is okay, right? The two climb is okay. Okay, then let's base on the two climb then. The first thing is we want to create a set called E. Let's maybe first call some set of EI. Let's say E equals to the union of EI, where EI is all equations with n equals to I. And here n equals to k plus c0 plus c1 plus until ck. So EI is finite for all I. Is that okay? So E is countable. I think this one is also okay. Okay. And then we show that S is all the solutions of some equations fx equals to 0. And here, remember, all this kind of S is the set of the algebraic number, right? So S is the set of algebraic number. That's right. And we know that S as is countable, we can list the E as E1, E2, E3, something like this. The equation. And let's denote Si is the solutions for equation EI. And Si is also finite for each EI. So S equals to all the union of Si. S is countable. S is countable, which means the algebraic number the set is countable. Ci here Ci should always be a integer. Ci cannot be a real number or rational number. It still doesn't. Yeah. Ci is inside Q. Ci is always an integer, so it's not possible that Ci be a rational number. It's already mentioned in the question Ci must be Q. And here, so you said that if Ci is rational number, can make it like the integer. So basically, Ci can only be integer. Ci cannot be any other rational number other than integer because in question it said Ci is inside Q. And our x can be rational or whatever, but we show that the set of s is countable. And we know that SC union S is equals to real number set which is not countable. So SC is not countable. And SC is a set of transcendental number, right? Wait a minute. Wait a minute. Wait a minute. Q is, I remember Q is integer, right? Q is integer. Oh, sorry, Q is, yeah, you are right. My first Q is rational number, but this two claim is still, oh, okay, then, okay, I just think that Q is integer, my fault, sorry. Uh, yes, you can do that because it's easy to multiply the common multiplier of all the, yeah, you can do that all the divisor so that you can convert all the rational number into the into the integer. So yes. Yes, that's not a big problem here. So suppose some C0 is A over B, then you can simply multiply B to all these sides. So that's not a big question here. It's not influence these two claims, so claim one, claim two. So that means this will not influence any proof in this system. Yeah, so basically you can just simply define a function which map from the equation to another set of equation where this equation will is in Q and to Ci for all the Ci is integer. This equation is easy to define and it's easy to find that this equation is what uh it is kind of onto. Okay. Okay, what else do you want to ask? If X is Okay, so you mean that X is something like A1 union A2 and union A3, and A1 equals to, let's say, A1, A2, A3, something like that. And or let's say, maybe let's use ABC is better. A, B, C, and B equals to B1, B2, B3, blah, blah, blah. C equals to C1, C2, C3. So all the three units is countable. So you mean how to show that X is countable, right? Then you can simply set X equals to A1, B1, C1, A2, B2, C2, blah, 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 blah. And you can call that maybe X1, X2, X3, blah, blah, blah. And if you want, you can additionally define a bijective function from X to N so that fxi equals to I. Basically, you can just state that in this order: A1, A1, C1, and then A2, B2, C2, A3, B3, C3. Something like this. Is that okay? Yes, this is a theory. I think you have learned that in class, right? This is in some lecture note. So basically, X equals to union Xi, and if is countable if Xi is countable for all I. This one is in your lecture note, right? I remember you have learned that in class. Or if you want, I can give you a proof here. So basically, if we want x1, x2, x3, and there's many there. So basically, we have x11, x12, x13, blah, 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 blah. X21, X22, X23, blah, 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 blah. X31, X32, X33, blah, 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 blah. And X41, X51, blah, 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 X42, X52. And you can state this countable like X11 and X12, X21, X13, X22, X31. Do we do that in this order? In this order, you can list everything in order, and then you can make that as the map it to natural number with its index. This is the official proof, and I think you have learned that in class. So if you want, you can directly use this. I will give an official solution to publish the official solution there. So this one will not count because my handwriting is bad. But everything is inside PDF, so you can read that later. Okay. I feel that's all for today. If no other question, I will stop here.